The oxidation of propan-1-ol can form propanal and propanoic acid. The boiling points of these compounds are shown in table 1. So we can see that propanoic acid has the highest boiling point, then propan-1-ol, then propanal. In a preparation of propanal, propan-1-ol is oxidized dropwise, is added dropwise to the oxidizing agent, and the aldehyde is separated by distillation. Explain with reference to intermolecular forces why distillation allows propanal to be separated. So it must be that for distillation to work, it must be that propanal has the lowest boiling point because it can come off first. So we need to say why in terms of intermolecular forces propanal has the lowest boiling point. So, and we're remembering we're oxidizing propan-1-ol to get to this. So we would say propanal. So propanal, remember, is an aldehyde like this with a C double bond O and a H. Propanal so it has permanent dipole forces between the molecules. So intermolecular forces, so between the molecules. And then propan-1-ol, which remember has the OH alcohol functional group, would have hydrogen bonds between the molecules. So propanal has a lower boiling point as dipole forces are weaker than hydrogen bonds. What that means is it will boil first and it will be able to be collected by the distillation. Give 2 ways of maximising the propanal obtained by distillation of the reaction mixture. So what we want to do is avoid collecting any propan-1-ol. So we want to keep the temperature. Remember that thermometer is in there. It's in there just at where the vapours pass into the condenser. So we want to keep it just below the boiling point. We want to keep it below the boiling point or at the boiling point of propanal, but below the boiling point of propanol. So we could say that we want to keep it, if we have a look back at the table, we want to keep it somewhere around 49, 50, but not up to 90. And the other thing we want to do is cool the distillate as we collect it to avoid it evaporating. So that means cool the liquid coming out of the condenser, and that will prevent loss of it. So that is our propanal. So we want to keep it in an ice bath. That will increase our yield. How could you carry out a simple test tube reaction to prove that you have propanal and it does not contain any propanoic acid? Now, to test for propanal, we could do tolerance, but that wouldn't prove it doesn't have any propanoic acid. The way to test it doesn't have any propanoic acid is to try and test to see if there is some propanoic acid. And the test for carboxylic acid is to add sodium carbonate or sodium hydrogen carbonate. If there is no effervescence, there is no propanoic acid. So our question continues on the next page. We're trying to find the enthalpy of combustion of ethanol. So remembering that ethanol C2H5OH could combust to make CO2 and water. It says 400 75 milligrams of ethanol, increase the temperature of, and this is important, 150 grams of water. Let's work out our delta T. So we're going to do 40.2 minus 25.1. If we do that, we're going to get 15.1 degrees C. And that water was here, 150 grams, with our thermometer in, 15.1 degrees C. Our fuel is down here, burning underneath, and this is our 457 milligrams down here. So when we do Q equals MC delta T, remember that this is all about the water. So we had 150 grams of water with a specific heat capacity of 4.18, rising by 15.1 degrees. So you want to get your calculator out and type that in. And you'll get an answer, because C is in joules, you'll get an answer in joules. You need to know how many moles of ethanol it took to create that heat. So it took 457 milligrams, but remember, to work out moles, you need to turn milligrams to grams. Then we need to add up the MR of ethanol, which is 46. We'll do that on our calculator. 9.93 times 10 to the minus 3 moles. So 9.93 times 10 to the minus 3 moles to create 9,467 joules of energy. So 9,467.7, turn it into kilojoules, divide by 1,000 or times 10 to the minus 3, divide by how many moles you used, and you'll find the number of kilojoules per mole. So on my calculator, that's coming as 952.985. Now I'm going to give it to the, as asked, appropriate number of significant figures. So I'm just going to scroll up, 3 significant figures there, 3, everything's been given to 3. So I'm going to round this to 3. So I'm just going to write 3, oops, not in highlighter there, 3 significant figures. So I want to give it to 3 significant figures, which would be 953. But then the other thing I'm going to remember to do is that enthalpy changes, if the temperature rises, are exothermic. So I need to put a minus sign in. Now we've got the next part of the question, which says a mixture of isomeric alkenes is produced when pentantuol is dehydrated, and it says pentwanene is one of the isomers produced. So we're attempting to turn it into pentwanene. So we're removing water, so we're doing an elimination here. So it wants us to draw out our mechanism. Just going to draw out the functional group carbon to start off with. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep. And put our alcohol group on. I'm going to put a lone pair on there. Off it goes to pick up a proton from the acid catalyst. And so we've protonated our leaving group, our alcohol. So we haven't actually affected the rest of the molecules, so just draw that bit out. But we've protonated the alcohol, which makes it a better leaving group. So it's going to leave by breaking the bond between carbon and oxygen. Now that's going to create a carbocation here. At this point, because I know I want to make pentwanene, I know, if we have a look back at our structure, if I want to make pentwanene here, that I need to create the double bond between carbon number 1 and carbon number 2. So I'm going to draw out carbon number 1 because that's where the next functional group is going to be created. So I'm going to lose a proton from carbon number 1 and use the electrons in the bond to create the double bond. And that is going to give me a double bond at the end because we've lost a hydrogen off carbon number 1. And we've used those electrons to satisfy the other carbon by creating the double bond, pentwanene. It says a pair of stereoisomers is also formed. Now remember, stereoisomers, when we're talking about alkenes, is EZ. Right, so the choices are, so the one that would make EZ is if we actually went to pentuene. So we could have this one would be the E and this one would be the Z. Now what we need to realise is that the E is a much more symmetrical shape, and so the any kind of polarity created from the presence of the double bond is more spread out, whereas on the Z, with the groups all coming down to the same side, we're creating a sort of uneven distribution of the electrons in the molecule. So it would be E that is the less polar. And then it says, explain how this type of stereoisomerism arises. Well, it arises due to restricted rotation around the double bond. And it also only arises when each C of the C double bond C has two different groups.